Okay, so today we're going to be talking about basic electrical quantities. And because we have a lab today as well, I'm probably going to work less example problems than I normally would, but I'm going to say that largely what we're talking about today will be a review on what you learned about current, voltage, power, and all that kind of good stuff in the 120 series. So I would argue that you hopefully don't need too many examples. So the first thing that I want to talk about is charge. Circuit analysis at its most basic form is really just an understanding of how charge is behaving in any given circuit, okay? There are two charge-related phenomena that we are going to talk about at length: current and voltage. But before we do that, I want to just set some kind of ground rules here. So charge, kind of classical definition, is the ability, if I could spell, of a material to interact with an electromagnetic field, which I'm going to say EM. Okay. Now, I am more than aware that the overwhelming majority of you haven't taken Physics 202 or anything like that, so probably don't have the foggiest clue what it is I am talking about when I'm talking about electromagnetic fields. That's perfectly reasonable, okay? The very, very little amount of E&M we're going to talk about in this class could be covered in roughly half an hour. So if there's something that doesn't make sense, I'm willing to go into greater detail on it. But for the most part, we're going to use electromagnetic fields as kind of a catch-all to explain just a couple of things that there really isn't a better way to go about explaining, all right? So the ability of a material to interact with an electromagnetic field means that they can experience force from that electromagnetic field. That's all that I'm talking about there, okay? Charge is a quantized property. Which means that you can't break things down below the fundamental unit of charge, okay? So everything that we're going to deal with has an integer number of electrons and or an integer number of protons. And since those subatomic particles have a fixed amount of charge, then we can only deal with integer variations on that, right? So I'm going to say Q is the elementary charge having a value of 6.0218 times 10 to the negative 19 coulombs, where the coulomb is the fundamental unit of charge named after the discoverer of the electrostatic force. Okay. This is the same number that you guys learned. Actually, it might not be the number you learned in the 120 series. You might have learned how many electrons composed 1 coulomb of charge, which would have been like 5 point something times 10 to the positive 18. Yes. Is it big C or little c? No. Big C. So protons have positive Q and electrons have negative Q. But everything is based on that number there. Okay. So let's talk about those charge-related phenomena here. Which one do you want to talk about first, current or voltage? Current, all right. So electrical current is the rate at which charge moves through a system. That's it, okay? So inherently, charges that are in motion have an associated current, okay? So if we have a charge that's standing still, we have no current. If we have charges that are moving, we have some current. And mathematically, we can express this as current, I, as a function of time, is the derivative of charge as a function of time with respect to time. So this is going to be our definition of current. It corresponds very well with the definition that you guys learned in your Engineering 120 series, total amount of charge passing a point divided by the total amount of time it takes that charge to pass a point is equal to the current. It's the exact same relationship, but because we're big boys now, we get to use calculus, okay? Current in this class has two different components, right? It has a magnitude, which is what you're used to dealing with, and it also has a direction. And I would argue that if you don't specify both the magnitude and the direction, you have not defined the current properly, all right? You really need both of those pieces of information. So what I mean by that is that if we have a generic circuit element, element A, and I say that there is a current of 3 amps flowing through it, I've only specified its magnitude, but we really don't know what else there is about it, right? The direction of current is critically important in circuit analysis. So I need to also always include an arrow to indicate its direction, all right? So if flowing from the topmost terminal through element A and down is 3 amps, what would this same current be represented as flowing up through the element instead? Negative 3 amps, great. Right? Absolutely fantastic. So we can see here from this simple example that if we're ever given a negative current, in order to convert it to a positive current, because sometimes that'll make our math a little bit easier, not carrying around as many negative signs, all we have to do is change the direction on the arrow, right? So changing the direction of the current flow is the same as multiplying it by a factor of -1. Those two are the same operation, just one is mathematical and the other is graphical, but they mean the exact same thing. So you can see here that we represent currents in a circuit using, again, a magnitude, 3 amps in this case, and an arrow indicating its direction. That's pretty standard across all the different electrical engineering conventions. For voltage, as we'll talk about in a little bit, things can get a little weird depending on where you're physically located in the world. The next thing that I think I want to talk about is current sources, okay? So in your Engineering 120 series, you guys dealt with batteries or voltage sources for practically every circuit that you were given. To my knowledge, current sources never once even popped up anywhere. So we probably need to spend a little time defining it. So the first current source that I want to talk about is going to look like this. This is what's called an independent current source. Independent DC current source. Okay? So its magnitude is given as IS, or whatever numerical value is associated with the source, right? So if this were a 5 amp source, you wouldn't see IS, you would see 5 amps next to it. And the direction of current flow is indicated by the direction of the arrow. Seems, I hope, fairly straightforward, okay? Anybody have any idea what this word independent might mean in this case? Perfectly reasonable. If you don't, spring something new on it. Any thoughts? Ian?
Regardless of like what circumstance the circuit itself is under, it's going to have the same current.
That's exactly correct. So an independent source provides a fixed amount of current in this case because it's a current source. So another way to think about this is that it provides a fixed amount of current regardless of what voltage appears across its terminals. So a 5 amp current source will deliver 5 amps regardless of whether it's short-circuited, whether it's connected to a resistor, whether it's connected to a capacitor, whether it's open circuited like we have here. The voltage across it means nothing. There is no relationship between the current being provided by that source and the voltage that is appearing across the terminals of that source. So that's another way to look at that independence, okay? So we know exactly how much current is flowing through it. We know nothing about the voltage that's appearing across it. So I'm going to write that down. Current is known. Voltage is unknown. All right. So we are going to spend the first 6 weeks of this class dealing effectively with only DC sources. But we are going to spend some time towards the end talking about AC sources and all that kind of good stuff. So I'm going to go ahead and give you guys the symbol for that now, okay? So for an AC current source, it's going to look practically identical, except that there's going to be a little tilde or squiggle in there. And that squiggle really just represents the fact that the current changes with time. And so I would argue that its magnitude, IS, should also change with time. Which is why I'm saying IS is a function of t. So this guy is an independent AC current source. And it provides a fixed time varying current. So what I mean by it provides a fixed time varying current, because that might sound a little strange, is let's say if this was a sinusoidal source, it would give a sinusoid having a particular magnitude at a particular frequency and a particular phase angle, regardless of what is connected to it, right? So it's always going to be 5 cosine omega t plus 30 degrees if that's what is provided, okay? So it can vary between +5 and -5, but it's never going to go outside of those bounds because it is a fixed current source. We're going to have two more current sources here that we'll talk about. And these guys, generally speaking, are going to tick you off. That's perfectly reasonable. You'll get used to them, is the best that I can say. So the first of which I'm going to define like so. Okay. So instead of our circular symbol, we now have a diamond. All right. Diamonds are going to be used for dependent sources. All right. So this is going to be a dependent current controlled current source. So I'm going to say that its magnitude is K times IX, where K is just a scaling factor, okay? That has units of amps per amp, or you could just as easily say that it has unitless units, okay? So what a dependent current source does, and this is where you guys are going to, yes? X, yes. So what's happening here with this particular current source is that it is referencing a current elsewhere in the circuit. So the current flowing through some particular element, and then it is scaling the amount of current that's flowing through that element by a value of K. Okay, so this is why it gets a little wackadoo, because a current somewhere in an entirely separate area of the circuit winds up controlling how this source operates, okay? For this class, these are going to be purely theoretical exercises, right? Actually, current sources in their entirety are going to be a theoretical exercise, right? Voltage source probably makes sense to most of us because we can hold them in our hand, right? It's a battery for a DC voltage source. An AC voltage source is one of these plugs all around the room, right? A current source in and of itself actually doesn't exist, legitimately. We can create transistor-based circuits that very closely model the behavior of these current sources that we're talking about in this class, but they're never going to be spot on. So all the current sources that we're dealing with in this class really are purely theoretical concepts, but they'll help us with understanding some things and modeling for those of you who decide to spend more time with me and progress in the EE career, okay? Let's see. So our fourth current source, and this is the last of the current sources, sorry, it scrolled, is going to have effectively the exact same symbol because I just really feel like confusing you guys. This one will be a dependent voltage controlled current source. And so I'm going to say that the magnitude is lowercase g times Vx. So G is our scaling factor here. Having units of amps per volt. So this current source provides a fixed amount of current that depends on a voltage elsewhere in the circuit. This is how we model transistor behavior for the most part. well, how electrical engineers model transistor behavior for the most part. We, as a class, aren't going to model transistors one bit because we don't cover transistors here. But it's where they're most commonly associated with is transistor circuitry, particularly the small signal model, which again means nothing to the overwhelming majority of you guys. All right. So to recap current, it is simply the rate at which charge flows through or passes a particular point in a circuit, or I is equal to dq by dt. Current has both a magnitude and a direction. Both of them are extraordinarily important. Okay. We represent currents with their magnitude and their direction when we're doing circuit analysis. And we may be dealing with circuits that contain current sources, which are providing us some fixed amount of current, which is denoted by the magnitude associated with the source, and the direction of those fixed amounts of currents are given by the arrow that's enclosed in the source. We okay with currents? Anybody got any questions, comments, concerns? All right, now let's talk about voltage. I have two definitions for voltage, one of which mathematically is probably going to seem really confusing, but it's helpful to think about what it physically means. And then the other one is the one we're actually going to use for the overwhelming majority of this particular class. Okay, so let's talk about the one that might be a little bit confusing. So mathematically, voltage, I'm going to call it VAB for now. Will be the integral from A to B of the electrostatic force, actually I take that back, the electric field, vector E, dotted into some differential line element, dl. Again, I am overwhelmingly aware that practically none of you have any clue what I'm talking about here. That's perfectly reasonable, okay? I'm gonna change my electric field vector into something potentially a little bit more recognizable. I don't know why I wrote my bounds of integration on the wrong side of the integral a moment ago. So the electric field is nothing more than the electrostatic force divided by the charge that's provided, okay? Multiplied or dotted into this differential line element. And I'm going to take that 1 over q factor and move it outside of the integral because it's a constant. And so that's going to leave me with 1 over q times the integral of force dotted into length. So if we throw that 1 over q bit away, what is that integral? Work. So voltage is energy transfer or work being done. Really, all voltage is the work that is required to move charge Q from point A in the circuit to point B in the circuit. That's it. All right. So it is the work done per unit charge to move charge around the circuit. In your physics class, if you've taken Physics 202, you may have heard of a concept called the electromotive force, where an electromotive force does exactly what its name applies. It moves electrons, or it moves electricity. Voltage is an example of an electromotive force. So a way that I like to think about voltage is it's what provides the push that causes current to flow. Without a voltage present somewhere in the circuit, there will never be current, a net current flowing in the circuit. There's always going to be a little bit of electron movement due to thermal energy and stuff like that. But you need to actually apply a voltage somewhere to see any real, and by real I mean on the order larger than nano amperes of current flowing around. Oh, I guess I should have mentioned the unit of current is the ampere, but you guys should all know that from your engineering 120 class. Sorry. Speaking of units, we can pretty easily see here that the unit of voltage is the volt, which is defined to be 1 joule per coulomb, because it is work or energy per charge. The second definition, and it's the one that I find a lot more useful in actual circuit analysis in practice, is voltage is the difference in electrical potential energy between 2 points in a circuit. So I'm going to attempt poorly to draw a battery real quick. So if you look at your average Duracell battery or whatever, you're going to notice that on one side, there will be a plus sign. And on the other side, there will be a minus sign, giving us the positive polarity terminal and negative polarity terminals of our battery. Okay? So if I had a AA battery, what voltage is associated with that? 1.5 volts. All right. So what that means is that the positive polarity terminal of that battery is at an electric potential that is 1.5 volts higher than the negative polarity terminal of that battery. Okay. So we don't know whether or not the negative polarity terminal of that battery is at 0 volts or 87 volts or whatever. We have no frame of reference at all when we have an isolated voltage source like a battery like that. All we know is the difference between those two terminals, which is exactly the voltage supplied by that battery. So just like we did previously, we have a magnitude that we need to pay attention to, and now we also have to have a polarity instead of a direction, right? If I change the polarity, so let's look at a generic circuit element, and I find that there's a 5 volt drop, positive polarity on top, negative polarity on bottom. How would I express that voltage with a positive polarity on bottom, negative polarity on top? Negative 5 volts, right? So how many of you ever accidentally measured a negative voltage in your 120 classes on something? What did you do to fix it? Flip the leads, which means you reverse the polarity of your multimeter. That's all you're doing here, okay? To get rid of our negative signs, we simply swap the polarities of our element. or really we swap it, no, we don't swap the polarity of our element because our element probably doesn't have an associated polarity. We swap the polarity of our voltage. Sorry, I misspoke there. All right. So this is the convention for voltages that I prefer, actually. We have a magnitude and we have well-defined polarity. Positive polarity terminal denoted by a plus sign, a negative polarity terminal denoted by a minus sign. There's also something called a double subscript notation, okay? So if I had an element, let's call it B, like so. This is terminal 1, this is terminal 2. I could have a voltage V12, and I could have a voltage V21, and they are of equal magnitude, but opposite polarities, okay? I don't know that there's going to be any specific instances that I'm going to give you where a double subscript notation will pop up per se. But if you're studying online and all that kind of good stuff, I just want you to be aware that this is another way that voltages are represented. So the first number or character in the subscript is the positive polarity terminal. And the second number is the negative polarity terminal, which is why I said if I change the order of the subscripts, it's the same as changing the polarity of the voltage. For those of you, again, who progress into circuits 2, etc., this is going to be quite a big deal when we get to three-phase circuits, just because they're so complicated without doing something like that. Lastly, another way to represent voltage, this is done largely in Europe, is we might have some voltage magnitude, I'm going to call it V, and then we would have an arrow pointed from the negative polarity terminal to the positive polarity terminal. I don't like this one at all. I'm never going to use it. If it has an arrow, to me, it has something to do with current. That's just the way I learned it. So I'm giving it to you guys in case you watch some random YouTube video from a European fella trying to talk about voltage drops and all this kind of stuff. You might see that notation. I will never use it. I make too many mistakes. Okay. So my preference is the one on the far left for the overwhelming majority of applications. Excuse me. All right, so let's talk about voltage sources now. So we know how to represent a voltage in a circuit. Voltage sources, there are going to be several. This guy is a battery. The long electrode is associated with the positive polarity terminal. The short electrode is associated with the negative polarity terminal. This is likely what you guys saw in the overwhelming majority of problems in your Engineering 120 series. Okay? A battery is an independent DC voltage source. A more generic representation of a DC voltage source, which is the one that I prefer because there's no ambiguity. You could never accidentally confuse it for a capacitor. Would be this guy, right? I guess I'll put this as VS. So this is a generic independent DC voltage source. And effectively what's going on here is the positive polarity terminal is the one denoted by the plus sign. The negative polarity terminal is the one that's attached to the minus sign. And then the potential difference between those 2 points is whatever VS happens to be. Justin.
Let's say as you use a battery and the battery drains, and as the battery drains, the current went down, would that be a dependent DC voltage? Like as you use the battery in the day, it's less and less current.
Okay, so you're 100% correct that as you utilize a battery, like a real physical battery, the longer you use it, the amount of current that is able to be output by that battery changes. The reason why that current changes is because the voltage drop across the battery actually changes as well. So like a fully charged AA battery probably has somewhere between 1.55 and 1.6 volts across its terminal. And a fully discharged AA battery is just going to be somewhere around 1.4. And so all that really means is it isn't able to sustain current anymore, okay? We are going to talk about practical voltage sources in about 2 weeks. So effectively, all of these guys are ideal cases, even our representation of a battery, meaning we are making the assumption here that the voltage that's being provided by these sources is a constant value, either constant, well, in these cases as DC sources, a battery gives us 1.5 volts forever. We know that that's not actually true, but this is just a theoretical model to kind of help things out. What we'll find, and again, we'll talk about this in lecture 9 of this class, I believe, is that we can correct these ideal voltage sources to behave more like a practical or realistic voltage source by simply putting them in series with a resistor, where that resistor limits the amount of current that can flow, okay? So for instance, in your engineering 120 class, probably the first several class meetings, I know I harp about 120 a lot because most of you guys should be coming out of that series pretty fresh. Before you soldered on the barrel jack to your battery pack, you were probably told on multiple occasions never to leave the batteries inside that little plastic battery pack and then just toss it into your bag. Anybody know why? Anybody accidentally melt a battery pack? You didn't melt it.
But if we didn't solder them, by the way.
Okay.
It can't be soldered. But if there were to be a short connecting the batteries together, then they would all discharge through the wire with no real.
Yeah, that's effectively right. So it's been a while since I taught 120, so I guess you guys aren't soldering them anymore. My apologies. Back when I was teaching it and you physically soldered the barrel jack onto it and all that kind of stuff. But yeah, so effectively, if you have those 6 1.5 volt batteries all connected in series, inside that battery pack with the leads just kind of hanging out, you've got 9 volts of electric potential. If and when those 2 wires touched each other, you would form what's called a short circuit, or just a path of very little resistance. Okay, we're going to prove that it's not exactly 0, but it's a very, very small number. So if the batteries were ideal, that short circuit would cause an infinite amount of current to flow out of that battery pack, right? Because our batteries are not ideal, there's a fixed amount of current that could possibly flow, what's known as the short circuit current. So we're causing a short circuit fault. And for a AA battery, that's somewhere on the order of a couple of amps to maybe tens of amperes, okay? So it's not a whole heck of a lot, but it is enough to cause those batteries to heat up so much that they will absolutely melt that plastic. Now, I have a job outside of tech. I work 1 day a week for Sabre Building Systems by Selection out of Bossier City, Louisiana. And what I do is I work on battery energy storage containers. okay? Those battery energy storage containers, how many of you guys are familiar with a Tesla Powerwall? Couple of people. Okay, so what a Tesla Powerwall is it's this battery unit that you connect to your house. And so it's a kind of an alternative energy source. You typically charge it up with solar cells. And in the event of a power outage, this big battery can power your house without having to consume fuel like a generator would, okay? I make Powerwalls roughly half of the size of this room. So the voltages that we're getting out of these battery systems are usually somewhere between 1100 and 1500 volts. It's actually a whole bunch of batteries connected in series to form a rack. And then we tie those racks together to be in parallel, and we'll able to generate very large amounts of power. So like we have a system out in the Mojave Desert that is supplementing the Los Angeles Water and Power District's huge solar farm out there. So I think it was like 130 some odd buildings, so it's probably close to a $15 million project. Well, in the event of a short circuit fault, we expect to see currents flowing on the order of 400 kiloamps, 400,000 amperes, okay? So these little bitty battery cells that we have, short circuit them, it can be arguably dangerous. It's a really good way to start a small fire. Short circuiting the big battery systems that I work on is a really good way to cause an explosion and kill a bunch of people. Like there's been issues with some systems not built by me or the company that I work with at all, but in Korea where shoddy manufacturing and cost cutting has led to multiple fatalities in these systems. So anyway, all that to say, what we're working with in this class are theoretical models of idealized voltage and current sources, right? So in practice, absolutely, we should expect to see degradation over time where the voltage and current levels go down. But in this class, we're not going to worry about that too terribly much, and we are going to address it to some extent in a couple of weeks with the concept of practical voltage and current sources. All right, so the independent DC voltage source we have shown here, and the battery as well, provide a fixed amount of voltage regardless of what else is connected to the circuit, right? So this is a case where we exactly know what the voltage is, but that is in no way, shape, or form related to the amount of current that's flowing through that element, okay? So it's the exact same situation as our independent current sources, except the roles are reversed. We know what the voltage is, we have no idea what the current is. Our AC current source, or excuse me, AC voltage source is effectively the exact same symbol, except that now there's another squiggle in it, letting us know that the voltage varies with time. Then we have our two dependent voltage sources. So again, the arrow symbol always lets us know that it's a dependent source. So we can have a voltage controlled voltage source where we would have K times Vx is our magnitude. Again, K is just a simple scaling factor that has units of volts per volts in this case, or it can be considered unitless. And our last voltage source is going to be a current controlled voltage source where R is a scaling factor having units of volts per amp. All right. Any questions about voltage before we move on to power and energy? Yes, ma'am. Certainly, I apologize. I don't know if I can get both things on the screen at the same time though, but yeah.
Do you have a favorite class to teach?
Yes, it isn't this one, which nothing wrong with that. Like this is legitimately my second favorite class to teach. I like teaching the E&M classes because that's what all my PhD research was on. So I'm like real passionate about that stuff. But literally right under that is this class. I've taught this class the first 3 years I was here. I taught it every quarter, including the summer. Last year, I taught it in the fall and the summer. I wasn't able to teach it in the winter and spring because as program chair, I had to move to some other stuff because we had some holes to fill. And this year I plan on teaching it every quarter but the spring. So I teach it a whole heck of a lot. I like it.
Have you converted anyone to electrical engineering?
I don't know if I single-handedly have done so. I'm sure I've contributed in some ways. I've also worked with several biomedical engineering students to help them get a minor in electrical engineering because the EE concentration is no longer offered for whatever reason. And it seems that having a concentration in either electrical engineering or mechanical engineering helps a biomed engineer get a job in a much more quick time frame. Pure biomed engineering jobs are few and far between. It is what it is. All right, can I scroll back to the all right, so as I said a moment ago, any questions regarding voltage or current before we move along to power and energy? All right. So power and energy are very closely related, so we're going to cover both in the same go. So power is the rate at which energy is, I'm going to put in parentheses here, or quotation marks, excuse me, consumed. And I say that in quotation marks because we don't really consume power, we convert, or we don't really consume energy, we convert its form, right? So electrical energy can be converted into heat by way of resistance, which is what we're going to talk about next class period. And that's probably the most common application that you guys are aware of. So that's like literally how a space heater and all that kind of stuff works. You have this long section of nichrome wire. You pass an electrical current through it by applying a large voltage across it. All of that energy that's being transferred gets converted into heat, and a little fan blows it out into your living space so that you're not so chilly in the winter. That is a classical example of converting electrical energy into heat. So power is the rate at which energy is consumed. And mathematically, power can be thought of as the derivative of work or energy with respect to charge multiplied by the derivative of charge with respect to time, which is a fancy way of saying voltage multiplied by current. So P is equal to IV, exactly what you guys learned as freshmen. Energy then, and this is kind of circular logic here, if power is the rate at which energy is consumed, we will consider energy to be how much power is consumed over a fixed amount of time. Mathematically, that looks like W is equal to the integral from T1 to T2 of E of T dt. So those are our word definitions and mathematical definitions for power and energy. The next thing that I'm going to talk about here is what's called the passive sign convention. And it is either going to click to you guys, and that'll be fantastic, and this class will go easily and smoothly, or it's not going to click and you're going to get wildly frustrated. Unfortunately, it's going to be one of those two things. I'm going to try to explain it to you to the best of my ability, okay? So let's say that we have a generic circuit element. Like so, call it element A. And element A is carrying some current I in this direction. And element A has a voltage drop across it with this particular polarity, okay? So we could say that the current is flowing into the positive polarity terminal of element A. Right? So when current flows into positive polarity terminal, the element is absorbing power and energy. Okay. So this is true regardless of whether or not the voltage and current magnitudes are positive or negative. Okay. So in this instant, the power absorbed is simply multiply the product of V and I. Okay. Now let's take that same element I'm going to apply that voltage V in the exact same way, but now I'm going to change the direction of I. So in this case, I would consider that the current I is flowing into the negative polarity terminal and out of the positive polarity terminal. Okay. When current flows out of the positive polarity terminal, the element is supplying power and energy. So I'm going to say down here, P sup is now V times I. So we can relate these two quantities pretty easily because the only difference between them is the direction of current flow, right? So I could say that in my first example, the power that is being supplied is just negative the power that's being absorbed because the direction of the current is in the opposite direction, right? So P supplied is negative P absorbed is negative V times I. And for my second example, P absorbed is negative P supplied is negative V times I. Those are really the same things, just looking at it from a slightly different perspective, okay? The reason this is called the passive sign convention is because under the passive case, when everything is happening to our load, so which is what I'm considering where the current is flowing into the positive polarity terminal, we have a positive sign generally associated with the absorbed power, okay? There will be problems on your homeworks and your exams where you'll be asked to calculate the amount of power supplied or absorbed by a particular element. And you will go through all of the math and you will get an answer. And then either web work or myself will tell you it's wrong. And it's because you got the sign wrong, because you misunderstood this. It's going to be wildly frustrating. I understand that, but it is actually critical that you get this down, okay? I am enough of a jerk on the exams to when I ask you whether there's power supplied or absorbed, I will put the same numerical answer on there twice, but once with a positive sign and once with a negative sign to make you have to understand this concept. I'm letting you be aware of that now, a month before you have to take any of the tests, so that you're fully aware. I really, really expect you guys to understand this. Now, during the tutoring session or when you're working an in-class assignment problem, which we're probably not actually going to have time to do today because I'm talking too much and all that kind of good stuff, I have no problem whatsoever re-explaining this over and over and over again, probably until the 8th or 9th lecture. After that point, I'm going to get a little frustrated that you haven't caught on. Not saying I won't still explain it to you, but I'll be slightly more of a jerk about it, okay? It's that critical where I would rather you ask the question than assume something and be getting it wrong consistently over and over and over again, okay? All right, so any questions about this? I want to, if we can, in lieu of doing the in-class assignment today, because I'm running out of time, I'm going to work one of the problems with you guys. Cheston, can you help me pass some of these out? I know your name, so I can put them in today. So what I would like to do, if at all possible, is finish this problem in the next 10 minutes or so that we can spend the rest of the class time talking about or doing the lab. So I'm going to write it down here. So my expectation for in-class assignment number 1 is that you sign your name on this sheet of paper, write what I write down, and then turn it back into me for participation points, effectively. All right. So for problem 3, we have the following circuit. entirely up to you. I would write it on the back unless you have a stapler or something. I don't know, but I did not. Thank you. Did anybody not get one? Thank you. Sorry, did somebody raise their hand back there? No, okay. Thank you for helping me out there, Justin. Fair, but I still appreciate it. All right. So for this problem, what I'm asking you all to do is to calculate the power absorbed by each element in this circuit. Okay. So let's look at the 36-volt source first. So this is the approach that I'm going to take, all right? We are being asked to calculate the power that is absorbed, right? That's what it says in the problem statement, right? So what I'm going to do is I'm going to take note of the voltage, and I'm going to take note of the current, both of their magnitudes, and then I'm going to take note of the direction of the current as to whether or not I need to apply the negative sign, okay? So when we look at the 36-volt source, my voltage is obviously 36 volts. How much current is flowing through my 36-volt source? 4 amps, okay? Is that 4 amps of current flowing into the positive polarity terminal or out of the positive polarity terminal? Out of. Since it's flowing out of the positive polarity terminal, I need to include a negative sign because the configuration that I have gives me this applied power, and I'm asked to find the absorbed power. That is the methodology to follow. So 36 times 4 would be negative 144 watts. Now let's look at element 1. What's the voltage drop across element 1? What's the current flowing through element 1? Is the current flowing into the positive polarity terminal or out of the positive polarity terminal? Into, which means I don't include the negative sign. And then I just repeat that for the other 3 circuit items. So let's look at the current controlled voltage source. You're right, 12 times 4 is totally 48. Thank you. So what is the voltage drop across my current controlled voltage source? This one's a little tricky, arguably. What does the magnitude say? 1 times Ix. What's Ix? 4 amps, right? So that's 1 volt per amp times 4 amps is 4 volts. All right, so my voltage is 4 volts. What's the current flowing through my dependent source? 2 amps. Is the current flowing into the positive polarity terminal or out of the positive polarity terminal? Out. So I need to include a negative sign. Negative 4 times 2 is negative 8. And the other 2 are fairly trivial, right? So both of the next instances is just the voltage times the current because the current is flowing into the positive polarity terminal in both cases. This is literally as hard as this needs to be. Yes.
Where did you get from there from?
So the 2 amps flowing down through element 3 has to have flown through the voltage source first in its path, right? So those two elements are connected in series. They have to be carrying the same amount of current. So that's where that 2 amps came from. We'll prove that statement that I just gave you in the next class meeting with a thing called Kirchhoff's current law. All right, I think that's enough talking out of me for today, unless anybody has some questions about this example or anything. We do have a lab. We have about 35 minutes to do it. So I'm going to pass some of these guys out.